Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss Reboiler function in a distillation system. The Reboiler. All machines have drivers. An internal combustion engine drives a car. Pumps are driven by turbines or motors. Jet planes are pushed by the thrust of an axial air compressor. A distillation column is also a machine, driven by a reboiler. It is the heat duty of the reboiler, supplemented by the heat content, enthalpy, of the feed, that provides the energy to make a split between light and heavy components. Look at this picture. The alcohol is called the light component, because it boils at a lower temperature than water. The water is called the heavy component, because it boils at a higher temperature than alcohol. Raising the top reflux rate will lower the tower top temperature and reduce the amount of the heavier component, water, in the overhead alcohol product. But what happens to the weight of vapor flowing up through the trays? Does the flow go up, go down, or remain the same? There are two ways to answer this question. Let's first look at the reboiler. As the tower top temperature shown in this picture goes down, more of the lighter, lower boiling point alcohol is refluxed down the tower. The tower bottom temperature begins to drop, and the steam flow to the reboiler is automatically increased by the action of the temperature recorder controller, TRC. As the steam flow to the reboiler increases, so does the reboiler duty, or energy injected into the tower in the form of heat. Almost all the reboiler heat or duty is converted to vaporization. The increased vapor leaving the reboiler then bubbles up through the trays, and hence the flow of vapor is seen to increase as the reflux rate is raised. Now let's look at the reflux drum. The incremental reflux flow comes from this drum. But the liquid in this drum comes from the condenser. The feed to the condenser is vapor from the top of the tower. Hence, as we increase the reflux flow, the vapor rate from the top of the tower must increase. One way of summarizing these results is to say that the reflux comes from the reboiler. The statement that the mass, or weight flow of vapor through the trays, increases as the reflux rate is raised is based on the reboiler being on automatic temperature control. If the reboiler were on manual control, then the flow of steam and the reboiler heat duty would remain constant as the reflux rate was increased, and the weight flow of vapor up the tower would remain constant as the top reflux rate was increased. But the liquid level in the reflux drum would begin to drop. The reflux drum level recorder controller, LRC, would close off to catch the falling level, and the overhead product rate would drop in proportion to the increase in reflux rate. We can now draw some conclusions from the foregoing discussion. The flow of vapor leaving the top tray of the tower is equal to the flow of reflux, plus the flow of the alcohol overhead product. The overhead condenser heat removal duty is proportional to the reboiler heat duty. The weight flow of vapor in a tower is controlled by one factor and one factor only, heat. An increase in reflux rate, assuming that the reboiler is on automatic temperature control, increases both the tray we're loading and the vapor velocity through the tray deck. This increases both the total tray pressure drop and the height of liquid in the tray's downcomer. Increasing reflux rates, with the reboiler on automatic temperature control, will always push the tray closer to or even beyond the point of incipient flood. Heat balance calculations. If you have listened my previous lectures and understood what you have listened, you will readily understand the following calculation. It is simply a repetition, with numbers, of the discussion previously presented. However, you will require the following values to perform the calculations. Latent heat of condensation of alcohol vapors equals 400 BTU per pound. Latent heat of condensation of water vapors equals 1000 BTU per pound. Specific heat of alcohol, vapor or liquid, equals 0.6 BTU per pound degree F. Specific heat of water equals 1.0 BTU per pound degree F. The term specific heat refers to the sensible heat content of either vapor or liquid. The specific heat is the amount of heat needed to raise the temperature on 1 pound of the vapor or liquid by 1 degree Fahrenheit. The term latent heat refers to the heat of vaporization, or the heat of condensation, needed to vaporize or condense 1 pound of liquid or vapor at constant temperature. Note that the heat of condensation is equal to the heat of vaporization. Each is referred to as the latent heat. The sum of the sensible heat, plus the latent heat, is called the total heat content, or enthalpy. Returning back to picture, we wish first to determine the reboiler duty. To do this, we have to supply 3 heat requirements. Heat 9,000 pound/hour of water from the 100 degrees Fahrenheit feed temperature to the tower bottom temperature of 220 degrees Fahrenheit. Heat 1,000 pound/hour of alcohol from the 100 degrees Fahrenheit feed temperature, where the alcohol is a liquid, to the tower overhead temperature of 160 degrees Fahrenheit, where the alcohol is a vapor. Vaporize 10,000 pound/hour of reflux from the 150 degrees Fahrenheit reflux drum temperature to the tower overhead temperature of 160 degrees Fahrenheit. Solution to Step A. 9,000 pound/hour times 1.0 BTU per pound degree F times 220 to 100 degrees Fahrenheit equals 1,080,000 BTU per hour. Solution to Step B. 1,000 pound/hour times 0.6 BTU per pound degree F times 160 to 100 degrees Fahrenheit plus 1,000 pound/hour times 400 BTU per pound equals 36,000 BTU per hour plus 400,000 BTU per hour equals 436,000 BTU per hour. Solution to Step C. 10,000 pound/hour times 0.6 BTU per pound degree F times 160 to 150 degrees Fahrenheit plus 10,000 pound/hour times 400 BTU per pound equals 60,000 BTU per hour plus 4 million BTU per hour equals 4,060,000 BTU per hour. The reboiler duty is then the sum of A plus B plus C equals 5,576,000 BTU per hour. The next part of the problem is to determine the vapor flow to the bottom tray. If we assume that the vapor leaving the reboiler is essentially steam, then the latent heat of condensation of this vapor is 1,000 BTU per pound. Hence the flow of vapor, all steam, to the bottom tray is equals 5,576,000 BTU per hour divided by 1,000 BTU per pound equals 5,576 pound per hour. What about the vapor flow leaving the top tray of our splitter? That is simply the sum of the reflux plus the overhead product. 10,000 pound/hour plus 1,000 pound/hour equals 11,000 pound/hour. Condenser duty is calculated as follows. 11,000 pound/hour times 0.6 BTU per pound degree F times 160 to 150 degrees Fahrenheit plus 11,000 pound/hour times 400 BTU per pound equals 66,000 BTU per hour plus 4,400,000 BTU per hour equals 4,466,000 BTU per hour. We can draw the following conclusions from this example. The condenser duty is usually a little smaller than the reboiler duty. Most of the reboiler heat duty usually goes into generating reflux. The flow of vapor up the tower is created by the reboiler. For other applications, these statements may be less appropriate. This is especially so when the reflux rate is much smaller than the feed rate. But if you can grasp these calculations, then you can appreciate the concept of the reboiler acting as the engine to drive the distillation column. Effect of feed preheat. Up to this point, we have suggested that the weight flow of vapor up the tower is a function of the reboiler duty only. Certainly, this cannot be completely true. If you look at this picture, it certainly seems that increasing the heat duty on the feed preheater will reduce the reboiler duty. Let us assume that both the reflux rate and the overhead propane product rate are constant. This means that the total heat flow into the tower is constant. Or the sum of the reboiler duty plus the feed preheater duty is constant. If the steam flow to the feed preheater is increased, then it follows that the reboiler duty will fall. How does this increase in feed preheat affect the flow of vapor through the trays and the fractionation efficiency of the trays? The bottom part of the tower in this picture, that is, the portion below the feed inlet, is called the stripping section. The upper part of the tower, that is, the portion above the feed inlet, is called the absorption section. Since both the reflux flow and the overhead product flow are constant in this problem, it follows that the weight flow of vapor leaving the top tray is also constant, regardless of the feed preheater duty. Actually, this statement is approximately true for all the trays in the top or absorption part of the tower. Another way of saying this is that the heat input to the tower above the feed tray is a constant. But for the bottom stripping section trays, a reduction in reboiler duty will directly reduce the vapor flow from the reboiler to the bottom tray. This statement is approximately valid for all the trays in the stripping section of the tower. As the flow of vapor through the absorption section trays is unaffected by feed preheat, the fractionation efficiency of the trays in the upper part of the tower will not change as feed preheat is increased. On the other hand, the reduced vapor flow through the stripping section may increase or decrease fractionation efficiency, but why? Optimizing feed preheater duty. Trays suffer from lost tray efficiency as a result of both flooding and dumping. Trays have some entrained droplets of liquid lifted by the flowing vapors to the trays above. This tends to blow butane up into the lighter propane product. Perforated trays always have some leakage of liquid through the tray deck to the trays below. This tends to drip propane down into the heavier butane product. When we increase feed preheat and the reboiler duty is automatically reduced, dumping increases, but entrainment decreases. If the trays below the feed point were working poorly because they were flooding, increasing feed preheat would improve their fractionation efficiency. If the trays below the feed point were working poorly because they were dumping, increasing feed preheat would reduce their fractionation efficiency. This picture summarizes this effect. If, for this tower, we arbitrarily state that the percent of butane in the overhead propane product is constant, then the feed preheat duty, which minimizes the propane content in the butane bottoms product, represents the optimum preheater duty. This preheater duty corresponds to the incipient flood point. The optimum feed preheater duty maximizes fractionation at a fixed reflux rate. Varying the heat content of the feed is an additional independent variable that an operator can use to optimize fractionation efficiency. An additional benefit of feed preheat is that a lower level temperature heat source can be used. If valuable 100 sig steam is required for the reboiler, then low value 20 sig steam might be adequate for the feed preheat exchanger. Multi-component systems. So far, all our examples have dealt with two-component systems, and many of our towers really just have two components. Also, we have assumed that the reflux rate is large compared to the overhead product rate, and many of our towers do run with a lot of reflux. But we can all think of distillation columns where the top reflux rate is small compared to the overhead product, and the overhead product itself consists of a dozen widely different chemical compounds. This picture represents such a column. It is called a crude pre-flash tower. Notice that there is no reboiler in this flash tower. All the heat input comes from the partially vaporized crude. Both the temperature and the percent vaporization of the crude are fixed. Hence, the external heat input to the pre-flash tower is constant. The pounds of vapor flowing to the bottom tray must also be constant. Now the overhead product of this tower is a mixture of 100 different components, ranging from ethane, which has a molecular weight of 30, to decane, which has a molecular weight of 142. Also, while the overhead vapor rate is 60,000 pound per hour, the top reflux rate is only 10,000 pound per hour. Consider the following. When the operator raises the top reflux rate, what happens to the weight flow of vapor going to the top tray? Recalling that the external heat input to this tower is constant, do the pounds per hour of vapor flowing to the top tray increase, remain the same, or decrease? The correct answer is increase. But why? Conversion of sensible heat to latent heat. When we raise the top reflux rate to our pre-flash tower, the tower top temperature goes down. This is a sign that we are washing out from the upflowing vapors more of the heavier or higher molecular weight components in the overhead product. Of course, that is why we raised the reflux rate. So, the reduction in tower top temperature is good. But what happened to the sensible heat content, the heat represented by the temperature of the vapors leaving the tower? As the vapor is cooler, the sensible heat content decreased. Where did this heat go? A small part of the heat was picked up by the extra liquid draining from the top tray. This extra liquid comes from the extra reflux. But the liquid flow through the tower is too small to carry away much heat. The main reason why the vapors leaving the top tray are cooler is vaporization. In other words, the sensible heat content of the flowing vapors is converted to latent heat of vaporization. But what is vaporizing? The reflux, of course. The sensible heat content of the vapors, which is reduced when the reflux rate is increased, is converted to latent heat as the vapors partially vaporize the incremental reflux flow. As the reflux rate is raised, the weight flow of vapor through the top tray, and to a lesser extent through all the trays below, except for the bottom tray, increases. This increase in the weight flow of vapor occurs even though the external heat input to the pre-flash tower is constant. The weight flow of vapor to the bottom tray is presumed to be solely a function of the pounds of vapor in the feed. Reduced molecular weight. A reduction in tower top temperature of 20 degrees Fahrenheit would increase the weight flow of vapor by roughly 10%. But the composition of the vapor would also change. The molecular weight of the vapor would drop by approximately 8%. The lower the molecular weight, MW, of a gas, the greater the volume that a given weight of the gas occupies. Gas volume is almost equal to weight of gas divided by molecular weight of gas. In this equation, if the weight of gas goes up by 10% and the molecular weight of the gas goes down by 8%, then the volume of gas goes up by 18%. The reduction in the tower top temperature of 20 degrees Fahrenheit does shrink the gas by about 3% as a result of the temperature reduction, so that the net effect of raising the reflux rate is to increase the gas volume through the top tray by 15%, that is 18% minus 3%. This results in a substantial increase in the top tray pressure drop, which can, and often does, cause the top tray to flood. This can happen even though the external heat input and feed rate to the tower have never changed. Internal reflux evaporation. The tray temperatures in our pre-flash tower, shown in picture, drop as the gas flows up the tower. Most of the reduced sensible heat content of the flowing gas is converted to latent heat of evaporation of the downflowing reflux. This means that the liquid flow, or internal reflux rate, decreases as the liquid flows down the column. The greater the temperature drop per tray, the greater the evaporation of internal reflux. It is not unusual for 80 to 90% of the reflux to evaporate between the top and bottom trays in the absorption section of many towers. We say that the lower trays in the absorption section of such a tower are drying out. The separation efficiency of trays operating with extremely low liquid flows over their weirs will be very low. This problem is commonly encountered for towers with low reflux ratios and a multi-component overhead product composition. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.